file. So that could be problematic. So I'm just going to fire up. The recording. It should be recording now on YouTube. And if you can't get in, I'm just going to post the YouTube live link into the CET236 channel, so the text channel, so you'll be able to you should be able to see it there. Oh, and I think I've got you on the wrong there we go. So let me just post that link into the 236 discussion channel. Actually, I'll put it in the materials channel, so it'll be there for a while. So if you can't get on to the stream that I'm live streaming at the moment, please try the YouTube link. The YouTube link will be a little bit delayed from the live stream from Discord directly. We'll just have to handle that. I'll try and make sure that everybody gets access. Okay, sorry about that. Let me just check. Is there somebody else coming online? Yeah, there are a couple of other people coming in. I just need to add them to the role. Okay, and we should be good. So welcome, as the screen should say for you. It's CET236, and my name is Peter Katsoukas. This is, I think the course is just called Circuit Analysis rather than Introductory Circuit Analysis. I like writing stuff on notes, as you can see on this page, and I've always had the problem in real life of not being able to record that stuff. If you could make sure you mute, please. Yeah, now Sam, I think you're the only one who's unmuted. Could you please mute? There we go. Okay. What I've found is, since we've been online, is OneNote allows me to write stuff on top of notes, either where I am now with the, and Ryan, can you mute please? On where I am now, I use a Wacom tablet to write. Yeah, let me mute you myself, maybe, if I can. There we go. Thank you, Ryan. The nice thing is it gets captured. So the way I distribute notes is I use OneNote as a way to distribute notes. You should have received an email asking you to, or letting you know about that. If you didn't get that email, or you want me to send it again, I can do that. Just let me know. Okay, so this is a slide that I'll probably roll out every week, and as we move through the semester, I'll grey out the top lines, and it'll give us some sense of where we're going. Looks like we have two breaks. The President's Holiday break on the 13th of February, and the Good Friday break on April 3rd. But other than that, that's the list. So we've got including finals week. We've got 14 weeks of lectures. Just to let you know, and I'll go into it in more detail as we get closer to it. I give exams. I give oral exams and midterms and finals. So that means you will come on to Discord with me, and I'll get you to answer questions live. And I found that's a good way of me getting to know each individual student a bit better and where they are with the material. And it also gives me a chance to give immediate feedback on what can be improved. But I'll talk a bit more about that as we get closer. This is the topic list. You can see there's some stuff grayed out in the bottom right down here. So let's go with the draw option. There we go. So yeah, this stuff here, that's unfortunately we won't have access to the lab, so we won't be able to physically use a multimeter, a power supply, a function generator, or an oscilloscope, and that's a bit of a shame. But one thing that I will continue to do, even when we're back fully on in person, is I hadn't started using LT Spice for simulation before, and now that I'm effectively forced to use it to simulate these equipment, I really like it. I think it's worthwhile for students to learn how to use it, and I think it helps students learn the material. And you can see all the other stuff that we've got to get through. I will point out two pieces of background. That's the other thing I meant to say. There's to get through some of this stuff, we need to understand complex numbers and linear algebra. So please bear with us while we go on. Okay, so as I said, my name's Peter Katsoukis. I have a background in electrical and systems engineering, that's control systems engineering. I did my bachelor's and master's degree at the University of Queensland in electrical engineering, and then I moved to the Australian National University in Canberra to do a degree, my PhD in systems engineering. I've also, since I've been in the States, I've had the opportunity to study a graduate certificate in system design and management up at the Sloan School of, actually it's a combination of the Engineering Systems Division and the Sloan School of Management up at MIT. And I was fortunate enough to have my employer pay for that, which was kind of fun. That's my email address. If you need to, I don't have official office hours. I'm only an adjunct professor. I don't have an office, and we're not on campus anyway, at least currently. So if you need to talk to me outside of class, feel free to click on that link and book office hours. At the moment, it's only showing dates on available times on I think it's Mondays, Wednesdays and Thursdays, but I will be changing that shortly to make some time available after class today, or maybe not today, but after class on Saturdays starting next week, and then some other times that I might be available during the week, maybe later in the evenings. I think the day the slots are currently only 9 to 5, so in case you need something to make an appointment later outside of normal business hours. So I gather, and like I said, I forgot the robotics or mechatronics engineering technology students in my poll that I put there. So it looks like we've got, what have we got? We've got MET, we've got one ME, we've got some CET students and robotics students. So welcome. What I thought we'd do is you could just, I'll just go down the list. In fact, I'll put the list on the screen so you can see it. Maybe it's not going to show up there. Maybe I've got to do that. And what I'd like you to do is just briefly unmute and let me know your name and your major, and I find it quite interesting. Maybe let us know what your favorite ice cream flavor is, or if you don't like ice cream, your favorite what I call IEU, ice cream equivalent units. I asked a class during the week, and somebody said they didn't like ice cream and they liked mango sorbet, and now I really need to get some mango sorbet because I think that sounds wonderful. But anyway, so I'll just work my way down the list, and if, like I said, if you could unmute and just let us know your name, your major, and your favorite ice cream or ice cream equivalent unit, IEU. So let's start with Bishop. Can you go? No? Okay, let's move on to...
Hello. Hi, my name is Jonathan Obando, and my major is robotic and mechatronic engineering. My favorite flower ice cream is chocolate.
Yeah, chocolate's very popular. Thank you, Jonathan.
Yeah.
So let's move on with, is it Christian? Can you unmute, please, and let us know?
Hear me?
Yeah, I can hear you.
Awesome. My name is Christian Mayorga. I am going for mechanical engineering technology, and my favorite ice cream flavor is chocolate as well.
Very good. Thank you, Christian. David Dubac, can you come online and let us know, please? So you're unmuted, but I can't hear. That's, yeah. It's a bit, yeah, it's a little soft, but I can hear you.
Okay. Yeah, my name's David. I'm a robotics major, and my favorite ice cream is cherry.
Ooh, cherry. Yeah, there's a good one. Thank you, David. Dylan, can you come online and let us know, please?
Hi, my name's Dylan. I'm a mechanical engineering major. My favorite ice cream is pistachio.
Yes, I had a student during the week who liked pistachio. Thank you, Dylan. Hugo, can you come online, please? I can't hear anything. You're unmuted, but... Not to worry. If it's causing a problem, just maybe type in the text channel, in the discussion channel. Okay, I'll move on to Hunter. Hunter, can you? Oh.
Is it working?
Somebody is. That's Hunter. Yes.
I'm Hunter. I just started doing CET, and it's a tie between chocolate and strawberry.
Very good. Yeah, I had a class during the week, and 3 people in the class liked strawberry. I was quite surprised. That's not a usual flavour, I think. But,
Depends on the brand, but some are a lot better than others.
oh yeah, definitely. I agree. It does depend. Great, thank you, Hunter. Joel, can you come online and let us know?
Hello.
Yep. Hello.
Hi, this is Joel. I'm a MET major, and I would have to say my favorite flavor is vanilla with Reese's peanut butter cup.
I forgot to say mine, and my favourite is actually there's an ice cream farm near where I live, and they have a thing they call Reese's Nightmare, and it's basically chocolate with, it's very good. I do like that. Okay, thank you, Joel. John, can you come online, please?
Good morning.
Good morning.
I'm John Wirtz. I usually go by Jack, so I might change the nickname later, but I wanted it there for clarity.
Okay.
I'm here for robotics and mechatronics and ice cream flavor. I think I'd have to go with mint.
Very good. Yes, my one of my daughters likes mint chocolate, mint choc chip. So yes, mint's a nice one. Okay, Kyle, can you come online? I think we heard from Jonathan earlier. Kyle Breton.
Morning.
Good morning.
My name's Kyle. I'm in the robotics major as well. I gotta admit, I'm not a huge ice cream guy, although some plain old vanilla is not too bad. And I do like black raspberry ice cream, provided that it's not ruined with little chunks of chocolate in it.
Very good. Very good.
That's the best I got.
That's good. Thank you, Kyle. That's good. Thank you. Leonardo? No? No Leonardo? Oh, you've got to do the other one. It's usually got a red stripe through the microphone. It's the mute button. So that's my mute. No? Still muted. Okay, we'll move on to Matt P.
Good morning.
Good morning.
I'm Matt Pereira. I'm currently a mechanical engineering major, and I would say my favorite ice cream is a Friendly's ice cream. It's the chocolate fudge brownie extreme.
Ooh. That does sound good. This is making me hungry, and it's too early in the morning for ice cream just yet. Thank you, Matt. Michael Matthews, can you come online and let us know, please?
Hi, I'm Michael. I'm a mechanical engineering technology major, and my favorite ice cream is mint.
Okay, mint, very good, thank you. Mike Fedora, can you come online, please?
Hello, my name is Michael Fedora. My major is mechanical engineering technology, and I would have to say my favorite ice cream would just be vanilla.
Vanilla, okay, very good. And Leonardo, were you able to get? Oh, Giovanni. Okay, can do that. Your CET. Ooh, coffee. Coffee is close to my. Sorry, I'm just reading Hugo's response in the chat. Coffee is up there. It's not my favorite, but it's one of the ones I get occasionally. So very good. So Leonardo, were you able to unmute? Yeah. Yeah. I can see you're speaking, but I can't hear anything. You might. That's okay. Nassem, can you come online, please?
Hi. My name is Nassim Abognim, and my major is computer engineering technology. My favorite flavor is strawberry.
Strawberry, very good. Thank you, Nassim. And Ryan, can you come online, please?
Hi, my name's Ryan. I'm a mechanical engineering technology student, and my favorite flavor is from a local creamery around here. It's coffee Oreo.
Ooh, coffee Oreo. Ooh, might have to try
It's delicious.
that. I might have to try that one. Very good. Thank you. Sarah, can you come online and let us know?
Yeah, hello everyone. My name's Saray.
Saray, sorry.
Yeah, Saray. I'm a CET major, and my favorite ice cream has got to be Dairy Queen's Oreo Blizzard.
Very good. Nothing wrong with one of those. Very good. Thank you. Spencer, can you come online, please?
Hello, everyone. I'm Spencer Kilby. My favorite flavor, I'm an MET major, and my favorite flavor would be salted caramel.
Yeah, the other one of my daughters, I think salted caramel would be pretty close to her favourite flavour. So Stephen Owusu, can you come online, please, and let us know?
My name is Stephen Owusu, and I'm a manufacturing engineering student. My favorite ice cream is vanilla chocolate.
Vanilla chocolate, very good. And Stephen Pasternak, can you come online, please? No? Okay, so let's leave it there. Thank you very much, everyone. I do like to hear everybody's voices. It's a bit hard to have everybody open mic all the time because, as you heard, some of the feedback that happens. But I will be using various. I will be asking questions during the class, and I do like to know that people can answer via voice, if possible. You don't have to. If typing is easier, we can do that. But I do like. You may see. I'll just pull this Discord window over a bit. You may see that there is a bot here. One of the other CET professors, Professor David Broderick, wrote a bot that talks to Discord, and I helped him work it out. Some of the functions anyway. He did most of the work. I twiddled with a few things. And one of the things that, in fact, what Professor Broderick does when he has in-person classes is he has a lotto ball with numbers in, and he assigns the whole class numbers at the beginning of the semester, and then when he has a question, he rolls the lotto ball and pulls a number out of the just like a lotto, and he asks random students a question, and so this bot has a bingo function, right? Which so I can, and I'm not going to ask Ryan a question, but the aim is to be able to randomly tag someone. And you don't have to answer. If you don't know the answer, you can say that. That's okay. But the aim is to make sure that I don't keep picking favourites, which is something I tend to do if I just fall into habits of calling on people. So I think having the bot is set up so that if you've been tagged before, you won't get tagged again until everybody else has been tagged. So Ryan, you've got a freebie, at least for now. Okay.
I thought I won bingo.
So let's actually start talking about some a little bit more about the, if you like, the red tape for the course. So the book I'm using, and a lot of the diagrams and everything, is the book by Dorf and I'm not quite sure how to pronounce it, but Svoboda? I don't know. But it's a pretty good book for this course. I have various supporting material. I didn't release anything for this one because we're all just getting to know each other. But what I will do for after this class is point you to some videos that I've done previously of some of the material. And the aim is that during class, I don't just talk at you all the time. I will talk at you a little bit like I am now. But the aim is to get you to engage with the material a bit better. And for me, the best way to do that is... the best way to do that, I just got to look at that one, there we go. The best way to do that is to actually work on the material, okay? Do problems, discuss the, discuss the answers, and maybe set up other stuff. Also, even though we're online, there are labs to be done, and as I mentioned earlier, that LT Spice is the way I'm getting people to do labs for this course, and I'll continue to do labs for this course. The textbook actually covers more than I really need for this course. And you can see the clouds on some of the chapters are the ones that really they're not that relevant for this course. The red ones, the red clouds, right? These ones over here, they're definitely not relevant. And then the blue ones are mostly not relevant. I do pull some stuff out of those, but mostly they're not. But we do get through the all the way through to chapter 7, and then chapters 10 and 11 are pretty good. A little bit of chapter 8. I briefly touch on the Laplace transform, but only in passing. You do not need to know about the Laplace transform for this course. And yeah, that's about it. So this is the way I set this course up is I will have a slide deck like this at the beginning of every lecture, which is just setting the stage and plotting our progress, giving information. The actual content of the course, the circuit analysis stuff, I have set up in separate topic slide decks, right? At the moment, I've got 4 topics here: basic concepts, series and parallel circuits, linear algebra background, and complex numbers background. Okay, so those slide decks are there. I think I forgot to upload these into Blackboard. If you would rather have them there, I can certainly do that.
I do think having them also on Blackboard would be helpful, especially when we have so many other classes with things stored on Blackboard.
Right, and I usually do that. I just think I've forgotten to do it. Did I? Oh no, there are all the topic slides there already. So I'm teaching several classes this semester, and I prefer giving students PDF slides rather than the PowerPoint directly. And I started looking at, I don't want to have to regenerate every slide deck from PowerPoint to PDF. So I thought about not doing it. And then I found a nice little VBA script for PowerPoint that runs through all of the PowerPoint files in a directory and spits out their PDFs. So I ran that, and then I could just not quite forget about it. I had to click OK a few times during it, but I didn't have to think about it. So I did regenerate all of the topic slides in PDF. So this is in Blackboard under course content. Okay. And you'll see the first 4 of the 4 that I've got in OneNote at the moment. Okay, so before I go there though, I do want to quickly run through the course syllabus. It's not going to give you much more information, but let's just have a look. So that's my name, that's my email address. That's my, it's actually a work number that comes into my computer, and it's technically a Skype number. So normally the best way to talk to me is via Discord, but if you do need to call, that's a number you can call. You can also text to that number if that helps, but again, just message me on Discord, might be easier. There are all the prerequisites. I believe, did I can't remember. I may have let somebody through without one of the prerequisites, but I think you all have them. As it says there, the textbook I'm talking about is recommended. It's not required. If you find it nice to have a textbook, that is the one I'm pulling all the notes out of. So I think that's fair to tell you that, but you don't have to have it if you find the notes that I give sufficient. That's the class time. I didn't release anything before this session, so don't worry about that review stuff for this session, but before next week, please review the study this next that I'll release after today's session. That's the link to my booking page. At the moment there's only a not actually doing anything. There we go. At the moment there's only a general consultation, and because this is we're here and I don't have any openings tomorrow, let's have a look at February, right? So there's Mondays, Wednesdays and Thursdays are the current slots. feel free to book any of those. As I said, I will open up some later times and some weekend times if that suits you better. And when that happens, that'll get you a slot on my diary, and I am usually very good about keeping that. If I have to reschedule, I'll email you and ask you to reschedule it. You have control over that time, so if you can't make it, please get in there and reschedule it at a time that you can make it. It won't let you book something that on a slot where I'm unavailable, unless I forget to put something into my calendar, which happens sometimes. So just be aware of that. Okay. Because I do one-on-one oral exams, the final exam will not be at the time that the university says it will be. I'll set up, if you look later on, there'll be another option up here, which will be CET236 exam, and I'll set up time slots for you to be able to do your exam at a time that suits you and me. I do not usually do exams during the Saturday course times. I prefer to have that time available for teaching, and so just be aware of that as well. Okay, where are we? There we go. So the grade, there's homework of 30%, lab of 20%, 2 short midterms and a final. And each midterm is 10% and the final is 30%. It should be perfectly possible for you to get 100% for the homework and 100% for the lab experiments. At the moment, you should see in Blackboard that there are 3, I think I set them up. The first 3 homeworks are available already, and I noticed somebody's already finished homework 1. And these are auto-graded assignments, and you should be able to see, I haven't set it up. So most of my assignments I set up to where you can have multiple attempts, and most of them I give everybody 3 goes at the assignment. So just because you do the assignment and get something wrong doesn't mean you can't have another go at it. And the trouble is, you need to have a go at it before the due date. I think I imported these, and the import doesn't carry the number of attempts across, unfortunately. Okay, so that's now set up. And it's just that's a good question. I don't know whether we have to finish it. What does it say? This test can be saved and resumed later. Okay, so that it should be okay. I would rather you think about the problem and get the right answer. The aim is for you to come to grips with material without me being there with these ones. So yeah, I think it should be okay. Only these first three are. I should talk about that too. Only these first three are auto-graded, but I'll talk about the others shortly. We're online now anyway, so obviously we can only submit stuff electronically. Please do not email me stuff. I stopped accepting emailed homework a long time ago because I lose it. At least if you submit it into Blackboard, everybody knows where it is. And the nice thing about being online is you get to keep a copy of your work. I don't lose it, and we can see the copy all the time because it's uploaded into Blackboard, right? So please do that. I don't penalise late work, except that you can't submit late work. Okay, you need to submit your assignments on time, and because they're all set up in Blackboard for submissions, you need to. I can set a deadline, and I can make the assignment disappear after that deadline, and mostly I do that. Having said that, before the due date, you can submit any accessible item 3 times, and I'm happy to grade the assignment 3 times. Okay. I haven't written it into the syllabus, but another thing I do is some students, a lot of students, for whatever reason, miss an assignment or 2. When it comes to the end of semester, I allow any student for no and 2 labs. Now there are about 10 of each in this course, so use them sparingly, and I usually only allow them to be used towards the end of semester. Okay. And I've already talked about midterms and finals. I'm okay with scheduling later exams if there's some, documented reason for the later exams. So please just be aware that I may change the exam if you do it later. I used to not use academic alerts, but I've found that unless I use academic alerts, I get students who fail more often. So I will use the academic alerts system if one of those 3 things is true. You fail to show up with one of the regularly scheduled sessions, 3 or more of our regularly scheduled sessions. You fail to hand in 2 or more homework assignments, or if you score less than 60% on either of the midterms. Okay, so the reason I do it is because I would like you to pass this course, and I want you to know earlier rather than later that you may be in danger of not passing the course. Please do your own work. There are lots of opportunities in class to collaborate with your peers. I am going to see if I can figure out breakout rooms in Discord. I noticed Professor Broderick was using his bot to set up breakout rooms, but I haven't used them myself. But I won't be using them today, but we'll see how we go. You can't tell, and I'm not wearing them at the moment because I've got my headset in, my earphones. But I'm partially deaf, so I'm open to any accommodations anybody needs. It's my personal view that all students benefit from accommodations, and I tend to make my courses as accessible as possible. I had it wasn't an accommodation so much, but when we were in the labs, one of the things that we do is we use devices called resistors, and the value of the resistor is shown by color bands on the resistor. And one of the students I had was colorblind, so he found it very difficult to actually figure out what resistor was what. So I made sure to pair him with somebody who wasn't colorblind, and got them to help him with at least sorting the resistors and getting the right resistor. That's the schedule. It tends to vary a little bit depending on what's happening, but you know, we'll see how we go. I think it's probably okay, but like I said, we'll see how we go. Okay, any questions so far? I haven't talked about anything to do with circuit analysis, and we're nearly an hour in. Oh well. Okay. And one thing I forgot to take off the slides is I did these for the summer 2019. I've updated them, but I've forgotten to take off the date, so I apologize. So let's start. Voltage, current, resistance, power, energy. There's a list of units, and dare I say it, I'm going to be using SI units in this course. I'm not going to be using speed in furlongs per fortnight, or I don't know, torque in foot-pounds or anything like that. I'm going to be using the metric system. So if you're unfamiliar with that, please get familiar with that. So length is in meters, mass is in kilograms, times in seconds. That's pretty normal. And the way I usually do stuff, I'll talk to this slide first, and then I'll branch out a bit. And there's various other related. So the ones on the left here, these quantities are pretty much the basic quantities. And then the ones here are what you might call derived quantities, right? So acceleration is meters per second squared, velocity is meters per second, frequency is per second or hertz, right? So there's various derived quantities, and the ones we're particularly interested in, I'm not so interested so much, we're interested a little bit in frequency. little bit in energy and power, certainly charge, potential, resistance, conductance, capacitance, and maybe not so much magnetic flux, certainly inductance. And the problem with some of that is scale, right? And so the other thing you need to remember or know what the values are the prefixes. So you've probably heard of a terabyte of memory. Well, that's 10 to the 12 bytes of memory. A gigabyte is 10 to the 9. A megabyte is 10 to the 6. A kilobyte is 10 to the 3 or 1,000. And then you've got centimeters is 1/100th of a meter. Millimeters is 1,000th. And micro, nano, pico, and femto. I don't tend to use stuff down at the femto level, but certainly we use these for capacitance values and in farads and inductance values in henries. And then we tend to use these for resistance values in ohms. Okay, so I'm just going to go off to the side here, and you've probably seen the video, so I'm not going to go through it completely. The key components for this course I write out as Viper, right? So it's a good acronym because I can remember it. And V is for voltage. The unit, right, is volts. The symbol is capital V. I, believe it or not, is current. The unit for current is amperes, and the symbol is capital A. Power is P. The unit is in watts, and the symbol is W. E is energy, and the unit is the joule, and the symbol is capital J. R is resistance, and the unit is ohms, and the symbol is capital omega. Related to resistance is impedance, and its unit is also ohms, which also has the capital omega. Okay, so they're the basic units, and there's some relationships here, right? So power is actually joules per second, right? And then these three are related. Oops. P equals I V. Right? The power is equal to the voltage times the current. Now, that is only true for direct current or constant current and constant voltage. There's if you're talking about AC, the sort of voltage and current that comes out of the power point in the wall, that also has a thing called the power factor, which we'll maybe talk about in the second half of the course. The other three here that are related are those three, and they're related using a thing called Ohm's law. Right? V equals IR. The voltage is equal to the current times the resistance. Now there's a couple of other things that I haven't mentioned that we do talk about in the course. And the two, I wrote them on the other slide. The two are related to resistance, sort of, and they are L, which is inductance, and it has a unit of henries, and the symbol is H. And we have capacitance, and it has a unit of farads, symbol capital F. You may see sometimes, certainly in the textbook, the phrase RLC circuits. Right? RLC circuits mean inductor and capacitor circuits. Right? So they've got all three sorts of devices in the circuit. Just quickly going to go for one more thing on this slide. We're going to be drawing circuits, right? And the symbol for a voltage is going to look like that, with a number. Let's call it. Let's maybe not call it A. Let's call it X volts, right? And that's a voltage source. You may also have a current source, which looks like this, and that would have the amperage, X amps beside it. A resistor is drawn like this, and it's going to have X ohms beside it. An inductor looks like a curly resistor, and it's going to have X henries beside it. And a capacitor looks like that, and it's going to have X farads beside. And the aim of this course is to be able to put these things together into a... oh, my head is in the way. Sorry. I should be... there we go. I can turn myself off. Or I can... maybe it'd be easier if I just scrolled this across. Right, there we go. I can scroll it across a bit better so you can read it. You're welcome. Okay. Yeah, there we go. So that's a quick overview of the stuff we've got to learn about. Right? And as I said, this is available in excuse me, in the OneNote notebook. You don't have to run OneNote. You should be able to access it using one of those two links that I just put into the materials. The top one here should take you to the web version of the notebook. You may have to log in using your CCSU credentials to see it. It's thinking about it. Maybe. Usually doesn't take quite this long. But basically it shows on the web this view, so you should be able to see my notes and everything in there. Thinking about it. Okay, I'll let that try and load up. This course runs on Saturday mornings from 9 a.m. until 10 minutes past 1, I think is the scheduled time. I don't know about you, but I can't talk for that long. I know you probably can't listen for that long. So what I usually do is during that time period, I usually take two 10-minute breaks. It's decided to say something's wrong. Anyway, so what I'm going to do is I'm going to ask, are there any questions so far? And we're going to take a 10-minute break. I'm going to put a timer up here. Which Google makes available. Before I start that, does anybody have any questions so far?
So far, so good.
Okay, very good. So I'm going to start the 10-minute timer, and I'm going to turn my head off and I'll mute myself for the 10 minutes, and I'll come back hopefully just before the 10-minute timer ends. Okay, so we'll start that up, and yeah, I'll see you in about 10 minutes and we'll continue. Okay, sorry, that disappeared on me. Took me a while to figure out where it was. Where are we? I need unmute wherever it got to. There we go. There we go. Okay. So I hope everybody had a chance for a bit of a break. I was doing some playing around. I wanted to debug that problem with OneNote on the web, which I managed to do, thankfully. So let me just show you what that looks like. Okay, so this is what it looks like on the web. It looks pretty similar to the app. So right, it gets the writing that I do on it. It means you don't have to install OneNote, but you do get access. So right, there's the stuff I just wrote up. So I encourage you to take your own notes, but I would also encourage you to use the notes that I give you through OneNote. All of these slides, as we saw, I haven't uploaded the ones for specifically for today into Blackboard yet, but all of the topics, the actual course material is already up in Blackboard. Okay. Does anybody have any questions now that we're back and you've had a chance to digest the first piece? No, I'll take silence as golden, so that's good. So let's just continue on. I do want to talk about a few other things as well, not strictly speaking about the course, but let's just continue. So one of the basic units we use in this course is current, and current, let's go with green, I think is my standard. Current is usually written as I, and I tend to use small letters for changing values or values that change with time, and capital letters for constants. You will hear me say the phrase DC, which stands for direct current, right? And the usual, at least for this course, the changing version is mostly about AC, or alternating current, where the current and the voltage is sinusoidal. Another piece that I didn't write up in my Viper acronym, because it doesn't fit with the Viper acronym, is Q. Does anybody know what Q is? And I don't mean QAnon. I'm going to go with my bingo card. And Matt P, can you let us know what Q is, if you know? If you don't know, that's okay. But unmute and let us know. No? Okay, I'll try somebody else. Nassim, do you know what Q is?
Forgot, sorry.
You forgot? That's okay. That's okay.
Professor, can you hear me now?
Yeah.
I was trying to unmute. It wasn't working. This is Matt.
Yeah, I can hear you, Matt. Go ahead.
I want to say it's flux, but I'm not sure if that's right.
Not quite, but that's a good answer. So let me try somebody else. And Christian, can you let us know what you think Q is? Like I said, it's not QAnon.
Not really sure.
No? Okay. We'll blow through all of our bingo. Michael Fedora, can you let us know what you think it is?
Isn't it charge?
It is charge. And that's the other Q. You're right. The one from Star Trek. Very good. So Q is charge. And this small q again, it's a changing with time. If I had a constant charge, I'd write that as capital Q. So the relationship between charge and current is this derivative, right? So the notation d by dt is the derivative with respect to time. I wish I could spell, it would be wonderful. And I hope everybody knows the acronym with respect to WRT, with respect to time. All right, so we're looking at how Q changes, and we're finding its slope as it changes with time. And so a way to estimate that is to say Q at T2 minus Q at T1 divided by T2 minus T1, and if you take the limit of that as T2 and T1 get closer and closer together, that's what the derivative is. This isn't a math course, but you should understand some of these things. The other way to write, I'd call that a differential equation. The other way to write that equation is as an integral equation, and that's what the equation on the left is. Right? You've got the charge, Q, is the integral from minus infinity to t of the current with respect to time. And if you want to capture all of the current that happened before time 0 into a number Q naught, or Q at 0, then you can do that last piece here where it says, right, this is just capturing everything before time 0. So that's a good question. What's the unit of charge? We haven't actually talked about that, so we should talk about that. Let me just finish writing this down before time 0. So the units of Q, one possible unit is certainly electrons. Right? We can count electrons. However, electrons are not an SI unit. So the SI unit is denoted, and this is for confusion, capital C, and the unit is called the coulomb. Okay? So amperes are equal to coulombs per second. And because electrons measure charge, and because coulombs measure charge, you can convert from one to the other. Does anybody know how to convert from coulombs to electrons and back again? I'm going to do my bingo game again. So David, do Do you have a thought about how to convert from coulombs to electrons and back again?
Not really, no.
No? Okay. So, John, do you, or Jack, I think you said you prefer? So,
if I had to wager, I guess, based on that formula there, you to convert from amperage to charge, you multiply your amperage by time.
oh, right. So yes, you would. That's correct. But what I'm after is I'm talking about you can measure charge in electrons, as was asked, and you can also measure charge in coulombs, which is the SI unit, the metric unit. And I was asking how you convert from charge in electrons to charge in coulombs. Okay, so, okay, let me see if somebody else, that's okay. So, Spencer.
A coulomb is 6.24 times 10 to the 18th electrons.
Very good. And where did you get the number like 6.24?
I actually work on circuit repair, and I have to measure picocoulombs every day, so it's just relevant to what I do.
Excellent. Very good. Right, so 6, and I wish I could write appropriately, so let me just clear that and write that 0 as actually a 0 rather than some squiggle. Right, so 1 coulomb of charge is equal to 6.24 by 10 to the 18 electrons of charge. Okay, and one of the, let me see if I can bring it up quickly. One of the sorts of questions I'm going to be asking, what is it going to be? One of the sorts of questions I'm going to be asking, let's just go with last summer, at exams, and that one. Let's see if I can open that one up. One of the sorts of questions I'm going to be asking is going to ask you to do the conversion. Right, so this was, let me just make it a bit bigger so we can all read it. Right, so this was last summer's midterm 1 for CET236, and I'll probably use a similar format for your first midterm. So this is the sort of question I might ask about this topic about charge. What is the current through a conductor if X electrons pass through a cross section in Y time? Right, so we've got X electrons, and I don't think I can draw on that. So what I'm going to do is I'm going to take a screenshot of that, and I'm going to come over here, and my dog has just got set off. So let me just make a new page, and let's call this example midterm question, and we'll get the picture from my screenshots. It's probably too big. Yeah, it's way too big. That's probably about right. Okay, so these are the sorts of questions. What is the current through a conductor if X electrons pass through a cross section in Y time? So the example is we have X electrons and Y time. And remember the relationship between current and charge is in this constant, right, the relationship was I equals dq dt, but where we've got constant values, we can just go with the change in charge versus the change in time. And that's effectively what these two are. The trouble is this charge needs to be in coulombs, right? So I need to convert that, and as we had, it's 6.24 by 10 to the 18 X coulombs, right? And then we can say that I equals 6.24 by 10 to the 18 X divided by Y, provided Y is in seconds. And then the other two questions are similar. They're just looking at the relationships between time, current, charge in electrons, and charge in coulombs. Any questions about that? I realise it's a little early in the semester to be talking about midterms, but I thought since it's relevant that we should at least start thinking about them. Where are we? There we go. Okay, let's get back to basic concepts. Much to say about voltage. The interesting thing, the most interesting thing as far as this course is concerned is Ohm's law and the power relationship, P equals VI. An interesting thing that happens when you substitute this into here and we get P equals I squared R, or we can also rewrite this as I equals V on R and substitute this into here and we get P equals V squared on R. What you'll find is a lot of power companies don't talk about the losses that they have in terms of V and I. And the reason they don't is because their power networks change voltage quite a bit around as they ship power to your house. What they tend to use is a thing called I squared R as the measurement of loss, about how much power they dissipate just shipping the power to your house. And that's where it comes from, right? P equals VI, V equals IR, so P also equals I squared R. And there's some more derivative relationships, and again P equals VI or P equals IV. Power is the derivative of work or energy. And there's a relationship that shows you that voltage is potentially, if you'll excuse the pun, the derivative of work with respect to charge. Okay, because our I is dq dt, the derivative of charge with respect to, yes, I apologise, Stephen. I've already talked about Ohm's law. The other version of Ohm's law that we will use in this course is V equals I Z, where now Z is an impedance, and in this case R is real valued, and in this case the impedance is potentially complex valued. So it's going to have a real and an imaginary component. So one of the really basic things in this course is how do we get resistance? And resistance is a physical property of a thing. Just about anything has resistance. And this is a way to calculate what the resistance of a particular thing is. The resistance, so I'll rewrite this equation a little larger, right? The resistance is equal to rho, which is the resistivity, which is a physical property of a material, times L, the length of the material, divided by, in fact, let me just rewrite that as capital L so it's different from rho. This symbol here is the Greek letter rho. So R equals rho L on A. So here's the length, A is the cross-sectional area, and rho is the physical property of the material. Okay, so if we know what material something's made out of, we know what the length of the material is, and we know the cross-sectional area of the material, then we can calculate what the resistance of that item is. And actually, I want to quickly see if I can grab that. And where's my that one? I want the other window. Oops, I got my wrong logo up. Let's get the right logo up. There we go. Okay, so I have my friend the Apatosaurus. Right, it's a toy. It's actually my daughter's toy. Right, he's got a tail. He's got legs. He's an Apatosaurus. These used to be called Brontosaurus, I believe. And I think it's changed again recently. They was originally called Brontosaurus, and then there was another dinosaur that was called Apatosaurus that turned out to be the same as Brontosaurus, but Apatosaurus had precedence, and it was published earlier. So that meant they had to start calling all what had been Brontosaurus Apatosaurus. And then for a while, the only dinosaur bones that were able to be called Brontosaurus was the bones in the Peabody Museum down in New Haven, because that was where the name came from. And then even more recently, they found actually that Brontosaurus is a separate species from Apatosaurus. So I really don't know whether this is a Brontosaurus or an Apatosaurus, or whether it could go for both. But anyway, I apologise for the dinosaur sidetrack. But what I want you to think about, the reason I have this silly toy out, is, right, I want you to think about if I stuck a meter between here, the tip of his tail, and here, the tip of his nose. Don't know whether, maybe that's in better. I want you to think about what would the resistance of this Apatosaurus be? Okay? How would you go about figuring out what the resistance of this dinosaur toy is? Okay, I'll go back to mini-me now. That's a bit scary, having me that big on the screen. Okay, let me do another bingo. And Jacob, do you have any thoughts on how you would go about figuring out the resistance of an Apatosaurus? Okay. Kyle, how about you?
So I'm sure there's a mathematical way of doing this based on like some kind of integral you take across the cross section and knowing the resistivity. But for us mere mortals, maybe I'd just stick a multimeter on it and see what it says.
Okay, both very good answers. I'm gonna meet you halfway though, right? Because I think I do like both of those. I think yes, you could cut this, right, do the integral approach and say, okay, this first little bit of his nose is really looks exactly like a cylinder, and if we cut it finely enough, then so that the L here is short enough, then it looks like a cylinder, and we can just keep adding lots of those very, very fine cylinders together and sum them up or integrate them up in order to get an approximation. That's one way. I agree. I would probably just do the measurement. But there's a midway approach, and my midway approach is to think, well, and so most of us are engineers or engineering technologists, so we're not really that interested in the finer details of the integration, but we do want to get a ballpark figure that may be right. Okay, so the way I'd go about it is I'd say, okay, well, let's think about his neck as one cylinder. Let's think about his body as another cylinder, and let's think about his tail as another cylinder. Even though I'm not going to integrate them. I can think about them being 3 separate cylinders, and there's just a cylinder here which has 1 resistance. There's another cylinder here which for his body, which has another resistance, and they're connected in series. And then I have another resistor for his tail as the last one. So just to draw that out quickly, right? I'd think about having his head and neck as 1 cylinder, and then maybe his body as a thicker, shorter cylinder, and then maybe his tail as another, this time longer, thinner cylinder, right? And this one has an area A1, a length L1, and it's all made of the same stuff, so rho is the same. This one has an area A2, a length L2, and rho is the same. This one has, let's just draw an area A3 and a length L3. And then, so the first section will have rho A1 on L1, rho L on A, sorry, wrong way around. Rho L1 on A1. The middle section will have rho L2 on A2. And the last section will have rho L3 on A3. And then we can just combine them into looking like 3 resistors in series like that, if we were drawing the electrical circuit, right? So that's R1, R2, and R3. Okay, but Kyle had the right answer, right? The real way, if you were going to do it in a scientific, really accurate way, you try and do the integration and do this sort of thing that I've just written up on the board up there, but do it very fine grained all the way along, so that the L's are so thin that the size of the Apatosaurus piece doesn't change much from one end to the other, so you can get an accurate approximation to the resistance of each part. Or physical measurement is very good too. That's a very easy way to do it. Or we could take this halfway approach where we want to get maybe we don't have access to a meter, maybe we can't reach the thing we're trying to measure. Maybe it's in an inaccessible area. We still need to think about what the measurement is, and so you can make a rough approximation. You can take the average neck diameter, the average body diameter, and then the average tail diameter, and figure out a way to approximate. Any questions about that? Okay. So that's one of the resistivity is one of the physical properties that we're going to talk about in this course. Another physical property is a thing called the temperature coefficient, right? And just because you have a resistor that is 10k ohms at the current temperature doesn't mean it stays that way. And in fact, most resistors are not thermally stable. So you have to take account of the variation. This is one reason why, if you've ever heard of the term mil-spec, why military specification electronics can be quite expensive is because you can't just use standard components. You have to use hardened or thermally stabilized components in order to have them work across a wider range of temperatures. One of the biggest problems I've seen with change in temperature isn't so much with resistors, but it's with batteries. You'll find that a lot of batteries don't work well at high temperature or at low temperature. I know my daughter, her older phone, she couldn't take it outside because it'd go from 70% charge to 0 charge within about 10 minutes if she took it out on a cold day. Anyway, what this physical property is called the temperature coefficient, and it's denoted alpha, right? And if you have a reference resistance, that is the resistance of at a given temperature Tref, and you know the new temperature T, then the relationship between the reference resistance and the resistance at temperature T is given by this: Rf times 1 plus alpha times the temperature difference, right? And both of these temperatures are in Celsius. And funnily enough, the alpha value is dependent on the sort of material. So here's our resistivity, that's our rho. Here's the temperature coefficient per degree C, there's our alpha. And these are some common materials, and some of them maybe not so common, and their resistivity and their alpha values. Some of them, here have there's a range of values given because it's not, the material can have impurities and can be in different configuration, right? There's different forms of carbon, for example. So the carbon range there is 3 by 10 to the minus 5 up to 60 by 10 to the minus 5. When you use the information on this table, particularly if you use one of the materials with a range of values, I don't care that much which end of the range you use, provided you write down what value you use. You could, like for hard rubber, you could use 1 by 10 to the 13th, or you could use 1 by 10 to the 15th, 100 by 10 to the 13th, right? Provided you say rho equals 1 by 10 to the 13th in your working, that is okay with me. You could, another way you could think about doing it is maybe you want to use the middle of the range. So for hard rubber again, maybe the value you use is 50 by 10 to the 13. Again, I'm not that particular about what value of rho you use. within that range, provided it's within the range of the material we're talking about, and provided you write down what value you use. Okay. So, any questions about that before I do anything else? So just as a, I'm going to get you to do some sample questions before we hit the midterm, but you'll notice that this last summer's midterm, the second question was about resistivity, and it gives X, Y, Z, and asks you to find the resistance, or it asks you to find the resistivity, or it asks you to how long is the object, or it asks you the cross-sectional area of the object, right? All four of these questions are using that rho L, R equals rho L on A. It's just which piece of the R equals rho L on A is unknown. Okay, so you're going to have to manipulate the equation around to get the unknown on one side and all the known pieces on the other. And then this is the sort of question that I might ask for the resistance versus temperature, right? Nominal value at room temperature, and temperature varies from T1 to T2. Find the range. What's the nominal resistance? What's the value of alpha? And then the question 10 here is a little bit trickier because the temperature is given in Fahrenheit, but the alpha value requires temperature to be in Celsius. Does anybody know the conversion? Let's see if we can go do a bingo draw. Jonathan, Jonathan O, do you know the conversion from Fahrenheit to Celsius or Celsius to Fahrenheit?
Yes. 1 Celsius is 33.8 Fahrenheit.
Okay. That's a 1 point, but how do you convert from one to the other? Is there a... Okay, let me go bingo again. Try somebody else. You did say what your preferred name was, Hugo, but I've forgotten what it was. Sorry. Giovanni, that's it. Giovanni, do you have a about how to convert from Fahrenheit to Celsius? No, that's okay. So let's have a quick. I'll just draw it up here on this slide here. Right. So just first, so degrees C and degrees F, the two sort of interesting points are 0 and 32, which is the freezing point of water, and 100 and 212, which is the boiling point of water. Right? So if you have your temperature in Fahrenheit and you subtract 32, yep, and then multiply by 5 on 9. Okay, so temperature in Celsius. So when the Fahrenheit temperature is 32, 32 minus 32 is 0, times 5 on 9 is obviously 0. When the Fahrenheit temperature is 212, minus 32 is 180, divided by 9 is 20, times 5 is 100. Right, so that's the conversion. I think the maybe have some Giovanni's answer with maybe the a bracket around the F minus 32, but yes, that's the way to do it. Okay, looks pretty good. And we did that. So I should have done something else. Let me just, I don't think I made it available yet. So let me just do this. I don't think I've done the I don't think I've done the newer version. Okay, what I'm going to do is I'm going to finish off this set of slides, and then we'll have another break again of 10 minutes, and then we'll I want to spend the remaining time. I'll maybe talk about the background material a little bit, but I do want to get you set up so that you can do the first lab. I want to talk about the lab. You don't have to do the lab today, but I do want you to get the lab done by 11:59 p.m. on Saturday next week. And there's a couple of ways you can do it, but I'll speak about that. But let's just finish off these slides first. Okay, let's just I just want to see that first. There we go, so I can see what you'll see. So we're talking about circuits, and these are relatively simple circuits, but we still need to, we still need to understand what each of them looks like. And the three across the top here are a resistor, a capacitor, and an inductor. Sometimes I'm going to draw all three of these just as a generic rectangle. Apologies for the, let's see if I can draw that a little more smoothly. Yeah, that's a bit better. Sometimes I draw all three of those as just a box and with an appropriate annotation as to whether it's a resistor, a capacitor, or an inductor. It'll depend on the units, right? So a resistor has units of ohms, a capacitor has units of farads, and an inductor has units of henries. We're not going to deal with capacitors and inductors for the first half of this course. I'm going to introduce them about halfway through because I want to deal with resistors. effectively what this course is going to do is we're going to do resistive circuits for the first half, and that involves just using real valued numbers. And then when we introduce inductors and capacitors, we're going to do the same operations and algorithms again, but this time we're going to use complex valued numbers. And that's about the only difference between dealing with resistors and dealing with resistors, capacitors, and inductors. And then the other circuit elements are power sources of one variety or another. And you can see all of the ones across the bottom. The first one over here is what I drew up before, and that's a current source, and it's called an independent current source. This is the round one with the arrow in it, and it's independent because its current doesn't change. It's always 2 milliamps. There are also these diamond sorts of current sources, and this is a dependent source. And dependent sources don't have a fixed value. They have a value that changes based on another variable in the circuit. So here this current is 4Vx, so it's related to Vx. That's for current sources. We also have the same thing with voltage sources. Voltage sources can be written like this. We often write it like this. So a battery is usually just a series of plates together. So we often draw a voltage source, a constant voltage source, as a battery like that. And again, these are independent voltage sources. They don't change, whereas you can also have a dependent voltage source which looks like this diamond. So one of the hardest things to get across in this course is how do you relate voltage to current? And you might think, well, that's really easy. That's just V equals IR, or V equals IZ if we're talking about complex valued impedances. Unfortunately, it's not quite that simple, because you've got to think about what you're measuring and what direction you're measuring it in. Right here we've got a device, say it's a resistor, it doesn't have to be, it's a generic box device, and it's got a current I1 flowing into A and therefore flowing out of B, and it's got a current I2 flowing into B and therefore probably flowing out of A. And the two currents are going in the opposite direction to each other. Right? So how do we figure out what's the relationship between the voltage across this device and I1 and the voltage across this device and I2? And in order to get around it, so one way to think about this is that I1 equals the negative of I2, right? I1 is going at whatever rate it's going from A to B, and I2 is going at whatever rate it's going from B to A. So you could think that, well, maybe one's going in the opposite direction, and maybe the opposite direction means there's a minus sign there. So, there's an approach that we use that allows us to define what the quote right way to do it is. It's purely a convention. It's not a law or anything like that. It doesn't necessarily come out from the physical properties, but it's a convention that helps figure this stuff out. Right, so here's the next step. So the first one was looking at the currents. Here now we're measuring voltages, and right, if we're measuring, I can't reach up there, but if we're right, one way, where's my pen gone? There it is. One way we could do this, right, is, let's get a black color maybe. If we had our meter, right, we've got our meter down here, and it's a voltmeter, and one way we could measure the voltage is we could connect our red probe up to here, the positive probe, and we could connect the negative probe, the black lead, up to B. And that would tell us what VAB is. Or we could take a meter and we could connect the red probe up to B, and we could connect the black probe up to A, and we'd get VBA. And you can see those two are different, and because we've put the negative probe on A for the first one, or for the top one, and the negative probe on B for the bottom one. So you can also think that VBA equals the negative of VAB. Okay, just sort of like the issue with the currents in the first diagram. So in order to get around that, there's this convention that we try and follow called the passive sign convention. I'm usually going to write that in shorthand as PSC, passive sign convention, as the acronym. Okay, and a device, a passive device, that is in this class a resistor, a capacitor, or an inductor, is said to adhere to the passive sign convention if the current flows into the positive side. And if the device adheres to the passive sign convention, then the power received by the element, or the power dissipated by the element, is P equals VI. If, on the other hand, we have the current flowing into the negative side of the voltage, then here the voltage and current are said to not adhere to the passive sign convention, not. And now the power P equals VI is the power supplied by the element or the power generated by the element, right? So the other one was received or dissipated, and if it doesn't adhere, then it's supplied or generated. And on this side of things, the power dissipated by this is equal to the negative of VI. And on this side, the power generated under this convention is the negative of VI. Okay? So the first assignment is purely about the passive sign convention, and it's just a multiple choice thing. Which devices supply 30 milliwatts? And you can see there's current directions indicated. Let me just make it a bit bigger so maybe you can see it properly. Right, there's current directions indicated, and there's positive and negative value voltages indicated. And you'll notice for all of these there is an option I don't know. And if you really don't know, please select that option. If you select that option, you will get 0.25 of a mark. Oh, maybe I think I set it up for 0.25 or 0.3. So basically, if you guess right at one of the other options, you have a 25% chance of getting it right. Whereas if you, so 25% of the time you'll get full marks, and the other 75% of the time you'll get 0 marks. But if you select I don't know, you're guaranteed to get 25%. And the reason I do that is I like to know when students don't know, because it tells me I need to work harder on that particular issue. So please feel free to do that. And there's various other questions about power supplied, absorbed, or what have you. Okay, it's a pretty simple question. And I think somebody has already taken it, so that's all right. Okay, so let's just go back here. So I've finished going through topic 1, which is the basic stuff, right? So as far as I'm concerned with those, and what I'm going to aim to do is take a break now, and when we come back I'm going to have a tutorial sheet available, and I'll see if we can do some tutorial problems, just quick ones, and then I'll see how we go. I might just talk about the lab, see how much time we have. Otherwise, if we've got time, I'll talk about series and parallel circuits. Notice I've also already talked about the passive sign convention, but I haven't really talked about series parallel circuits or KCL and KVL, Kirchhoff's voltage law and Kirchhoff's current law. But does anybody have any questions? Let's go with that for now. Let's just see if no, I'm not hearing anything. So let's take another 10-minute break, and when we come back, I'll aim to do at least those two things. I want to look at some tutorial problems, and then talk about the lab. Let me just put the timer up. Okay. So, does anybody have any questions about what we've gone through so far this morning? If not, I thought we'd do something a little different, and I want to talk a little bit about the labs. I've just released the first labs, right? And there's a lab sheet there, and as it states there, it unfortunately for some reason some PDF viewers don't highlight hyperlinks in the PDF, but this this page, actually this whole sentence has a hyperlink to LT Spice. Okay, and you should be able to download either the Windows version of LT Spice or the Mac version of LT Spice if you want to. I think I've got it. Where's it gone? LT Spice, there it is. So you can feel free to download that and run it on your local machine. Do be warned, if you're looking at tutorials for it on YouTube, the Mac version looks version. The Windows version has lots of icons and everything. Let me just show you the Mac version. If you're running a Mac, let me put it on the right screen. The Mac version starts up and there's virtually nothing, right? The Mac version, all of the functionality is in the right click menu. So you need to right click to edit, or draft is to get extra pieces, right? Just be aware for the Mac. The Windows version, it's a little easier to use. It's got icons for doing various pieces up here. It has the same, both of them have the same functionality. The Windows version and the Mac version have the same functionality. Just be aware. However, I wasn't going to go through that. I was asked that if you don't want to install it on your machine, or if you're running, for example, a Google Chromebook, go to the CCSU apps site and log into the Citrix gateway. And what you should see, and I forgot to check before we started today, if you go to desktops and you go to the Science Engineering Technology desktop, and I've got the local client installed, so it's not going to go through the let me get it on the right page, maybe. So you can see it. So this is what the Citrix server version for that Science, Engineering and Technology desktop looks like. And you should see LT Spice here. And it looks like it's setting it up for the first time. And I'm going to say no because it probably won't update properly. And as you can see, there's a little bit more functionality happening here than was available in the Mac version. Right, so I'm going to go with new schematic, and then I can add a resistor and maybe another resistor, and then I probably, oops, and I don't want to go up there, I want to, sorry, I just want to stop. Let's stop. And let's see if we can zoom out. There it is there. Maybe. Zoom in. I haven't used the is there a view? Zoom to fit is what I want. There we go. Right, and then I can draw wires between them. Just click there and connect there, and I can click there and connect there. Okay, and then we also have the ability to, we need to connect to ground up, maybe. Let's just go out a bit. So we've got some room, we'll connect to ground up. LT Spice always requires that you connect to ground up. So if your circuit doesn't work, it's possibly because there's no ground connected up. And then we also probably, wish it wouldn't do that. I need to escape before I start moving around. I also need to put on a maybe a voltage source. If I can figure out, I haven't used the Windows version in a while, so let's see if we can put in a new maybe it's just V, is it voltage? No. Why am I not seeing the ability to put on a new voltage source? I'm wondering whether there's a problem with that. Let me just see if I can do the same, what I want to do there, but with my version of LT Spice here. Okay, so I think what I want to do is, and then I want to do a resistor, right? And I can do that, and then hit escape, and then I want to draft a wire like that, and then I want to right click and draft a I've forgotten the I've forgotten how to get a the ground version. It's not a component. I remember that, but I thought it was in one of the other. There we go. There it is. And then we can go with, what was it, F3, I think, for wires. We can connect up ground. And then component, and I should be able to search for voltage source, right? So there's something wrong with the, and then F3 again to connect up the voltage source. Okay, I haven't set up any actual voltages, right? So I can set that up for 10 volts. I haven't set up any actual resistances. I'm going to set that to 1000, and I'm going to set that one to, I don't know, 2000. Okay, and now there's sorry, somebody's just... Yeah, I that was what I was expecting to be able to do, Jack, but when I looked in, I searched for that in the Citrix version of this, it didn't come up, whereas it did come up when I searched here. Let me just try that again. Yeah, so see, there's nothing in the list here, which means maybe I've got to set up a different library. Yeah. Right. So this me just running this now. Let me see if there's a configuration. Yeah, I can't see a place to set up. Okay, I'm gonna take that. If anybody does need to use the Citrix server, please bear with me while I try and debug that. I won't be able to do it right now, but I'll try and figure out what the problem is and get that fixed. But anyway, you can see both the Windows version and the Mac version work pretty similarly. The thing I have also forgotten is I need to write something. Oops. I need to write the SPICE directive, and I've forgotten what the right SPICE directive is. So let's just see if I can open up a recent one. Let's go with that one. Okay, so this is a later one, and it's not the one I want. So let's try draft 6 and .tran1. So let's just see if .tran1 works. And we'll just put that up there, and then we should be able to run it. And I don't have any. I'm going to measure that voltage there, so that shows up the 10 volts that I would expect. And I can also plot the current, which is on this right axis in blue, and that current, which is also on the right axis in red. Okay, and then I don't know whether I can get the total current. Yeah. I get that current, I get that current. I want to see this current as well. Yeah, so Jacob, in order to get in order to simulate, you need to hit that run button, and the .tran1 is needed to tell it to start up. It's the most basic parameter you can put in order to get it to run effectively. If I didn't have that in there, it'd complain about it. Okay. Yeah, so for example, if I if I don't have that in there and I hit that, it's going to say no analysis command found. So if you just put .tran1 in there, that'll get around that issue. Okay, let's just have a quick look at the lab. Maybe I'll do that over here. Right, so there's the lab. This lab is to ensure that you have LT Spice installed that can use it to construct simple circuits. You're required to upload the filled-in lab sheet and a screenshot of LT Spice with the circuit constructed. If you have problems with LT Spice, please make a booking to help resolve it. Okay, so I'm happy to offer IT support for some of this stuff. LT Spice is one thing you need to be able to do in order to do the labs. So please make a booking. As I said up here, it's this booking page, or in here it's under, I think it's tools for remote work maybe, and booking for exams and general consultations will take you there as well in Blackboard. Okay, let's just have a quick look at the lab sheet though. That's that one. Okay, so as I said, that line there takes you to the download page for LT Spice, and I want you to construct this circuit. It has a voltage supply and 3 resistors, and I want you to think about what the polarities and current directions are. So let's just think about that over here, and let's just I'm just going to go in and make a new page and say lab 1 notes, and let's just insert that screenshot in here and quickly talk about that. Okay, so remember we were talking about the passive sign convention, and one thing to note about this way to represent a constant voltage source is that this big plate, the long plate, is always the positive, and the short plate is always the negative. Okay, so we've already got our polarity for the voltage source defined, and it's standard for current to be indicated flowing out of the positive terminal of the battery or the voltage source. So in order for us to have R1 satisfy the passive sign convention, how do I label the polarities? Dylan? in order for R1 to satisfy the passive sign convention? Any idea about how to label R1?
So if it's a resistor, the power is dissipated, so the plus would be on the left side.
The plus
and
would,
the
that's
minus would be on the right side.
That's correct. So right, we've got a, let me get the drawing up, we'd have a plus on that side, so the current's flowing into the positive terminal of the resistor, and so that means the minus side is here. So VR1 is measured that way, and that's the voltage across R1. Okay? So then let's say that we have current flowing through R2 and R3. Right, and let me pick on someone else. So Joel, for R2, where would I put the polarity signs for measuring the voltage across R2, given that R2 has to satisfy the passive sign convention?
I think you would put the positive on the top and the negative under that.
That's correct, right? So we've got to have the current flowing into the positive and out of the negative. So for R2, to satisfy the passive sign convention, we've got to have that plus and that negative. Eek. Sorry, I shouldn't want to bingo there. I need to bingo back in Discord. And Leonardo, for R3, can you tell me where you think the positive and the negative signs go for R3 to make sure that R3 satisfies the passive sign convention? I don't know whether, did Leonardo have problems with his voice? Maybe if you could just type. Okay, let's try someone else. Oh, okay, he might be on delay. Okay, thank you, Jacob. Yeah, sorry about that, Leonardo. Yeah, apologies for the. I think the lag between YouTube and live is about 30 seconds. So I may have to dig into why that is. A colleague of mine, Professor David Broderick, uses Twitch to live stream his stuff, and he reckons the lag is much shorter there. But we'll see. I'm better set up. Our maximum capacity is 25 people for each voice channel in Discord. It used to be 50 when I started using it, but then they cut it back to 25. Oh, really? Okay. Yeah, it certainly used to be 50, but I think they've cut it back to 25 now, which is a bit of a bummer. Okay. Michael Matthews, did you have a thought about where the positive and negative side goes on the resistor, R3? positive on the left and negative. That's exactly right, because again we've got the current flowing into that side, right? So our voltage VR2 is measured that way, and our voltage VR3 is measured that way. Okay, one of the things you're going to see is, in this case, it's pretty simple, right? What's happening. It's going to get a bit more complicated quite quickly, and I'll just show you why. I'm going to take the same circuit, right? Okay, thank you for letting me know. I might get you to... yeah, that's correct. I did notice that there was a delay setting in there, Mike. I'm using a software called Streamlabs OBS, and that's also got a delay in there. I might see about tweaking that back so that the delay from me to YouTube is not as much. But I won't play with that now. I'll cause all sorts of problems if I do, I dare say. But I'll aim to fix that for next time. So one of the things we're going to do later on, very shortly, probably next session, is we're going to talk about current loops or meshes. And we're going to look at something like this, which is the current I1. And then we're going to also have another current in the other loop or mesh called I2. And then if we're just talking about loops, we could talk about that loop current called I3. Okay, so and you'll notice, let's just look at R2. You'll notice for I1 you've got the current flowing in on the top and out on the bottom. But for current I2 in R2, you've got it flowing in on the bottom and out on the top. And that's okay. You've just got to be careful with whether you're thinking about voltages with respect to I1 and the direction it's flowing, or you're thinking about voltages with respect to I2 and the direction it's flowing. It really is completely arbitrary, Jack. I tend to start on the left-hand side and go 1, 2, 3, 4, 5 across. I tend to do that, but it's not necessary. You'll see later on we'll get circuits with 2 or 3 or 4 voltage supplies, so there'll be a voltage supply on the left and a voltage supply on the right and up and down and whatever. So it is completely arbitrary. You just got to I think there was one case a while back where I had 2 R2s in the labeled in the diagram, and that caused a bit of confusion for me and for the students. So yeah, the numbering is completely arbitrary. I tend to go from the left and clockwise in terms of the numbering, but it depends on the geometry of the circuit. Okay, let's just go back and have a look at what Lab 1 is asking for again. So you saw how I set up the values for the voltage and the resistor values. You just right click and it gives you the ability to change those. Let's just have a quick look again, right? So I go here, I right click, and it lets me edit the resistor. And let me see if I can find that one. Here I can right click and it gives me the ability to change the value of the resistor. Okay, that's both in the Mac version and in the Windows version. And yeah, all I'm wanting you to do is to use this sheet and put in the voltage that you measure across R1, the voltage you measure across R2, and the voltage you measure across R3, and we're done. The main thing this lab is checking is that you have access to LT Spice. I think it will be easier for you if you install it on your local machine, but if you, for whatever reason, you don't have access to that, it is available on the Citrix server, provided I can figure out where the library is and how to change the library. And I'll post a solution to that if I find it later, hopefully later today. And then you fill out this sheet and then go to the lab, click on the lab title, browse your local files, find the PDF that you used for the to fill out for the lab, and then you're done pretty much. I do want to talk a little bit about labs, but I'll talk more detailed labs, but I'll talk about that next week. Just to start the conversation, I connected up, I also put in an Excel spreadsheet template for labs that I think is worthwhile thinking about. Let's just see if Excel will open up for me. Here it is. Let's just make it a bit bigger so we can read it. Right, so for this course, there's no need to have a lab partner, but the sorts of things that you want to put in there are the date, your name, the title of the lab, what the objective of the lab is, any data, write up the conclusions, and we don't have any real equipment. Maybe you want to say what version of LT Spice you're running. That might be useful in case there's a problem. But normally we'd put in the serial number and the model number of the equipment we're using, the power supplies and that sort of stuff. This isn't necessary for the first lab, but I'll talk about that in a bit more detail next week, and I might edit that one to make it more applicable to this this course. Okay. Any questions about the lab? I'm just going to have an edit of it, if it'll let me. Right, and I would like you to get the lab done by February 13th, so you've got 2 weeks. You can submit up to 3 times, and once February 13th has gone by, you will be unable to submit. Just a quick look, I tend to use rubrics for grading stuff, and the labs are all pretty similar. In this case, I need to say that you've followed directions, that you've entered the measurements. In this case, it's the voltage, current, the voltage and the current across the 3 resistors. And I don't think there's any questions. The only follow direction issue is whether you include a screenshot of yeah, Jacob. Well, because I'm streaming this to YouTube, that automatically records it to you to on YouTube. So I actually used to use Streamlabs OBS to record lectures locally, and then I uploaded them to YouTube later, so they were available. But I sometimes forgot, and this way, one of the reasons I'm streaming live now is because once I finish the stream, it's still there, and that link that I put in the materials link, so this one here, that that'll go here, and it'll show me, right, and it'll still be here. Yeah, Jacob. Right, so yeah, I'm going to stop that. Okay, so that's that should be okay. You're welcome. Okay, so that's the lab. There's, like I said, I think there's going to be about 10 labs. Oh, while I'm here, if I set up things in Blackboard, there's a really, and I set due dates in Blackboard, and I usually do. Blackboard has this thing called the calendar or assignment calendar. And you will see, and let me just take off the capstone ones. You will see that homework 1, which is I talked about earlier, is about the passive sign convention, is due by 11:59 p.m. next Saturday. So please take your time and try the passive sign convention homework. Based on the way things happened just now when we were talking about that lab and the passive sign convention relevant for the lab, it seems like, at least the people I talked to, they got the directions correct. So that first homework should be pretty easy. But anyway, there I have set up a few other things. So let's have a look at February. Yes, please. If you could upload everything into a single PDF, Giovanni, that would be good. Okay. Could I go over which one more time? The homework. Okay, yeah. So the let's have a look at the homework. Actually, before I do that, I'll just quickly finish off here, right? So here's the February, and you'll see that homework 1 is due next week. Homework 2 and 3 are due in 2 weeks' time, and the lab that I just went through is due also in 2 weeks' time. So have a look at those. Now, for the homework due next week, let's have a look at it. It's this quiz called the passive sign convention, right? And this is the first question. For some of these questions, you will get individual numerical values different for every student, but for this particular one, the answers are all the same. So which devices supply 30 milliwatts, right? So milliwatt, if it's a small m, so it's by 10 to the minus 3 watts. And let's see, we've got 10 volts and 3 milliamps, so 3 milliamps by 10 volts is 30 milliwatts one way or the other. 6 by 5 is also 30. 6 by 5 again is also 30, and 2 by 15 is also 30. So they're all numerically doing something with 30 milliwatts. The question is, which ones are supplying 30 milliwatts, right? So supplying 30 milliwatts, the passive sign convention is not set up, right? So is not adhered to if it's supplying 30 milliwatts, because if the device is supplying power, it's an active device. It's a battery or a current source or a voltage source. So that means we need to look at the 4 items here and see which of them, and there's 2 of them, which of them is not adhering to the passive sign convention. I think that should be pretty obvious, right? The ones that aren't adhering to the passive sign convention have the current flowing in to the negative side. All right, if it adhered to the passive sign convention, you'd have the current flowing into the positive terminal of the device. Is that enough to go over, Giovanni? And all the others are pretty much the same. Absorbing is the other way. Received is, this is about device B, so we need to figure out what the scale and what the sign is, and then what's the power delivered by device B. Again, we need to get the scale and the sign right, and what's the power delivered by device D, and again we've got to get the scale and the sign right. Okay. I just wanted to see, this one's multi-choice as well. Oh. So for some of the later ones where you've got to give a numerical answer like this one, and we haven't got over voltage dividers yet, so wait for next week. You will also need to put in the units, right? So instead of just giving a number, you need to give a number plus a unit. If you'll see each of these is worth 0.75 points. If you have a look at it and if you get graded and you only get, I think it's 0.5 points, you probably left off the units. So make sure you give the units in some of these later tests. So I uploaded earlier into the materials chat channel the PDF for the first tutorial. So let's just have a quick look at that tutorial. And won't have much time, but we'll spend a bit of time now just having a look at it. Right, so here are some of the sorts of questions that you need to have a look at. Right, question 1, what is the current through a conductor if 1.248 by 10 to the 19 electrons pass through a cross section in 10 seconds? Right, or question 2, what is the current through a conductor if, I should say, 1.248 by 10 to the 19 electrons pass through a cross section in 12 minutes? Right. How many electrons flow through a wire with 1 microamp flowing through it for 1 day? How many coulombs flow through a wire with 200 milliamps flowing through it for 1 week? And then, excuse me, how many coulombs flow through a wire with 400 picoamps flowing through it for the month of February? So what I'm going to try to do, and I don't know whether it'll work, is I'm going to try out the breakout room functionality. I haven't used it before. So let's just see. And what I'm going to do is I'll get the, I think there'll just be 3 breakout rooms. And what I want you to do is the people in each breakout room will talk about one of the questions that I've just put up. So, and there's going to be, I'll try making 5 breakout rooms. I'm not sure that functionality is working. But the top, if you look in Discord, the breakout room at the top will do question 1, the second one will do question 2, etc. Okay, so let me just see if I can okay, so I think I found myself in breakout room 1. So this room can, if you can do question 1 and have a look, okay? So this is Kyle, Jonathan, Christian, and Bishop.
Okay.
Okay, I'm just going to go to the other breakout rooms. And if you could have a look at question 1. Hi, this is breakout room 2. So Jacob, Joel, Leonardo, I've forgotten how to pronounce Saray and Stephen. If you can have a look at question 2, and I'll call everybody back in about 5 or 10 minutes. Hi, this is Breakout Room 3, so if the people in this room can have a look at solving question 3, and I'll call everybody back in about 5 to 10 minutes. Is that okay? David, Giovanni, Mike, and Nassim?
Sounds good.
Okay. Hi.
Which tab is it under on? I'm on Blackboard. I'm trying to find the assignment.
He sent it. He sent it in the materials.
It's in the materials, and it's also it's also under tutorials on Blackboard.
So it's the tutorial questions 1, just to clarify we're on the right.
That's correct. PDF? That's correct. Yep. So I think.
And this group is doing question 4.
You're doing question 4. That is correct. Okay. And I'll call you back to the main room in about 5 to 10 minutes. Okay.
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 And hi, this is Breakout Room 5, I believe. So if you could have a look at question 5 on the tutorial sheet, that would be good. The tutorial sheet is in the materials text channel on Discord. It's also available under the tutorials section in Blackboard.
Okay.
Thank you.
Okay, and I'll call you back to the main classroom in about 5 to 10 minutes, and I'll see if we can get people to give their solutions. Okay.
Which question did you say?
You can do question 5. It's below the table on page 2, I think, of the tutorial sheet or page.
Thank you.
Okay. Thank you. So, group 1, any thoughts?
I guess we have to.
Oh, good. Sorry.
You're good? Yeah?
Yep.
Okay. I'll go check on the others. So, Breakout Room 2, how are you going?
I'm still kind of trying to figure out how to solve it, to be honest.
Okay, that's all right. Keep going. Okay, how's this group going? Any luck? Everybody's muted, so you're not talking.
I'm still working on it.
That's okay. Keep going. I'll check with the next room.
Hello.
Hi, how's it going? Any luck?
Yeah, I think we figured it out.
Yeah?
Yeah, we got our answer.
Okay, cool. I'll just go check on the next room. Hello, how's it going? Any luck?
I'm working on it right now.
Okay. Okay, got about another 5 minutes or so. and I'll call everybody back.
Okay.
Okay.
Okay, we're all back, I think. That actually mostly worked. The people who were watching on YouTube didn't get put into a breakout room, unfortunately, so I'm going to have to get those people to join manually by themselves. I'll have to give them time to do that next time. So that's all right. Let's have a look at some answers. Does anybody from Group 1 want to speak up and give us your group's answer for for question 1?
Sure. So the question was the current through a conductor of 1.248 e to the 19 electrons go through a cross section in 10 seconds.
Mm-hmm.
And so you need 1 coulomb is 6.24 10 to the 18. So you have to divide the number it gives you by the number of electrons in a coulomb. That gives you the coulombs through that section in 10 seconds, and then amps is coulombs per 1 second, so you divide that by 10 more. And so that gave us 0.02 amps.
0.02 amps.
Or 0.2 amps.
0.2 amps.
0.2. That's what I meant to say.
0.2 amps. Does everybody agree with that? Can you see how that's happening? Right. So there's about a factor of 2 between those two numbers, 1.24. So 1.248 by 10 to the 19 electrons is about 2 coulombs, and then it's coulombs per second is the current, right, is amperes, so amperes is equal to coulombs per second. So if we've got 2 coulombs in 10 seconds, that's going to be 2 coulombs on 10 seconds, which seems about right. Okay, that's good. So group 2, how did you go? Did somebody get an answer for group 2? You'll notice the number of electrons. Yeah, go ahead.
Is it 2.77 milliamps?
2.77 milliamps. Could you explain how you got there?
Hold on. Where's the problem?
So
it's what is the current through a conductor? 1.248 e to the 19, right? That's question 2.
That's correct, and it's in 12 minutes. That's the only difference between this one and question 1. The time, the previous time was 10 seconds, and now it's 12 minutes.
Maybe.
Okay, so I'd go with 2 coulombs, which is that number of electrons, and then 12 minutes into seconds, 12 minutes, and then 60 seconds per minute. And that's the way I do that, and I can't do that in my head, so I'm going to go to Google, and so it's going to be 2 divided by 12 times 60, and you are correct. The number that comes up is 2.7. I'd actually call it 78 because it's 77 recurring, so the last digit should probably be an 8 just to round it up, but that looks correct. Thank you.
Yeah, so yeah, my bad. So I can explain what I did if you want.
No, that's okay. Yeah, go ahead. Try, you explain it. You go ahead.
So I used Q equals NE, where N is 1.248 e to the 19, and then E would be 1.6 e to the negative 19th. And then I did I equals Q over T. Oh, I didn't even give my answer to that. So Q is 1.9968 coulombs. And then, yeah, I equals Q over T, take the coulombs over the time. Time would be 12 times 60 for 12 minutes. And then, yeah, 2.77 milliamps.
Yep, very good. Thank you. So, group 3, you've got an answer for how many electrons flow through a wire with 1 microamp flowing through it for a day.
So I got 5.39 times 10 to the 17 electrons.
So 5.39 by 10 to the 17 electrons, okay?
You want me to walk through how I got that?
Yes, please. That would be good.
Okay. So I took the formula amps are equal to coulombs per second and rearranged it so the coulombs were equal to amps time seconds, and also added on the how many coulombs or how many electrons are in a coulomb. So I had 1 time 10 to the negative 6 amps times 86,400 seconds, and multiplied by the 6.24 times 10 to the 18 electrons.
Sorry, let me just write that down. So 1 by 10 to the minus 6 amps, and then the seconds was what?
86,400.
86,400, and then times the
electrons, the 6.24 times 10 to the 18.
Okay, and that gets you the answer you gave, yeah?
Yeah.
Okay, that looks pretty good. I will trust you that 1 day is 86,400 seconds. Sounds about
Hopefully
right.
Google didn't lie to me.
Yeah, I would wonder what would happen if Google started spreading fake news. That would be bad. Yeah, that's pretty good. That looks good to me. So group 4, any thoughts on the number of coulombs that flow through a wire with 200 milliamps flowing through it for 1 week?
We talked about how 1 amp is a coulomb over seconds.
Mm-hmm.
So you can find the coulombs by multiplying the amps times seconds. So we have in this problem 200 times 10 to the negative 3 amps going for 1 week. So we did 200 times 10 to the negative 3 times 1 week times 7 days times 24 hours times 60 minutes times 60 seconds to convert it to seconds, and we have 120,960 coulombs.
So 120,960 coulombs.
Yes.
Okay. That is probably not too far off. Very good. And so the next one is group 5. Can you say how many coulombs flow through a wire with 400 picoamps flowing through it for the month of February 2020? That's a trick question.
Yeah, I got an answer for it. I got 9.67 times 10 to the negative 4 amps, coulombs.
Okay, can you walk us through how you got there?
Yeah, so I used the equation I equals Q over T, and since we're solving for coulombs, I rearrange it so it's Q equals I times T. And then I figured out the amount of seconds that are in February 2020. So there's 86,400 seconds in a day, and then just multiplied it by 28 for the days in the month of February. And then multiplied that with the, I forgot the number already.
400 picoamps.
Yeah, and I multiplied it with the 400 picoamps, and then got 9.67 times 10 to the negative 4 coulombs.
So I did the same thing, except I multiplied it by 29 because this is why it was a trick question. It was a leap year in February 2020.
Exactly.
So it was 2,505,600 seconds times 400 to the negative 12, or times 10 to the negative 12, and then the answer I got was 1.00224 to the negative 6th power.
1.00224 by 10 to the negative 6. Yeah?
I vouch for him too. I realized I did the month of 2021, not 2020.
Okay. Yeah, sorry, I normally really dislike trick questions, so I do apologize for that. It does give me, I usually use the month of February because a lot of people don't know the rhyme about about how to figure out the number of days in each month. So yeah, and the other trick is that 2020 is a leap year, so you get that extra day on February. Okay. Any questions about any of that? I think those breakout rooms worked okay. I did hear a little bit of talking, so I think I'm going to continue using them as we go forward. I do have a series of tutorial sheets covering a lot of this stuff. I'm not going to do any more tutorial today. I think I will do more of that this sheet next week. So the resistivity stuff and the resistance versus temperature stuff, but I do want to do that together. I'd also want to talk about some of the background material before we do this next stuff, the linear algebra and the complex numbers. So that's all ahead of us. And then this sheet actually covers about 3 weeks worth of material, maybe 2.5. So I do want to cover. Yes, it is a long class. Normally this class is taught in two and a bit hour blocks on 2 days during the week, but this is the block of time I have is a little longer, and it's one block on Saturdays. That's why I take at least 2 10-minute breaks during that time. And it's also why I tend to finish the session a little earlier. Normally, if I'm doing this in person, the labs take a lot longer and I do them in class. In this online format, I'm asking you to do the labs on your own outside of the class session. Okay, because we've got the access to LT Spice, you don't have to have access to the lab to do it. So it's okay, I think, but it does make for a longer class if I use the whole time that I have available, and I don't tend to. So let's just do a quick... I am not. I should be sharing my screen, shouldn't I? Sorry about that. Oh, really? Yeah, sorry. I really should have been doing that. I really, really should make sure that happens. I apologize for that. Yeah, I do apologize. This is... I should have remembered to put it back on once we came back from the breakout rooms. My bad. So I've put the tutorial into OneNote. Okay. So you should see I wrote up as people were working through the answers. I've written up what they said, so you should have access to those, and just remember that one's probably wrong because it had the 28 days versus 29. Okay, let's just wrap it up. I just want to do a quick summary, and then we can leave a little early. Okay, so this is the stuff we've talked about so far: voltage, current, resistance, power, and energy. We've talked about the passive sign convention. There's still lots of other stuff we need to talk about, and I haven't added the other two things we've talked about today that are not in this list are resistivity and the change in resistance change with temperature. Okay, and let's just see somebody's message. Yeah, I forgot to put the screen back on, Ryan, after we came back from the breakout rooms, and yes, I'm only just started sharing it in the last little while. Yeah, you might have to click on either my name or the if you get the grid view, you'll see that there's a stream in the grid view, and you may have to click on the grid view, the stream box on the okay. Apologies for that. There's technical issues. So yeah, they're the things we've gone through today. The passive sign convention, voltage, current, resistance, power, energy. In fact, the things we've gone through are units in general. Resistivity, right? Remember your Apatosaurus, okay? As to how to find a shape. I think you'll find, in fact, let me just see if I can find that sample exam again. I don't have, it must be the second midterm. See if I can find the second midterm. Right, so, oh, that one's, I thought I had a more interesting question that basically mimicked the Apatosaurus. But basically I do have a question style that tries to find the resistance of a series of different geometrical shapes attached to each other, and each different shape or different object has a different material that it's made out of. So yeah, we've still got a bit to do, right? So I have gone through all the topic 1 notes, right? And the prime thing, the most important thing out of these notes is the passive sign convention. That is the most important thing. You will make mistakes in terms of sign in some of the more complicated stuff we're going to do shortly, and it is all because the passive sign convention is not adhered to when it should be. Okay, so think about the passive sign convention again, and look at homework 1. As I said, that's due this time, well, not this time, but 11:59 p.m. next week. And try and get lab 1 done. It's not due until 2 weeks from today, so but please try and get it done. If you have any problems, please ask about it during class next week. I'm happy to spend time on labs during class time. And then after that, next week we'll look at topic 2 and the topic 3, the background material, linear algebra and complex numbers. Does anybody have any questions?